Okay, today let's talk about function transformations. Functions can be transformed depending on what is going on with a given function equation. You can stretch your function graph or shift them around depending on what is multiplied or added or subtracted to the given function equation. Now, consider x squared minus 4. X squared minus 4 looks like, okay, here we go, this. Shall we look for the intercept? What is the y-intercept? Well, negative 4. Isn't that what the value of y is when x is equal to 0? Now, what are the x-intercepts? X squared minus 4 equals to 0, so that x squared is equal to 4. So you will get two different x-intercepts at positive 2 and at negative 2. Now, when this function is multiplied by something, so that imagine having 2f of x, so that you will be having 2 times x squared minus 4. What will happen to your graph? The graph gets stretched vertically by the factor of the given value, meaning that your entire graph here will be stretched vertically. And you can actually simply understand this as your function value, your y value will be doubled up. So that your negative 4, the y-intercept, will be doubled up to, what is it? Negative 8. What about the x's then? Well, nothing happens to your x. Your x's stays as where they were before. So that if you just regraph your 2f of x only using the xy intercept, then you will see that your graph is still a parabola, right? Will be stretched vertically. So it's increasing faster. Well, precisely twice as faster. If you graph them in your graphic calculator, you can actually trace some of the values, and you will see that, if, for example, if you compare 1, 1, right, with the new function value here, so if you plug in 1 here, what do you get? Don't you get 1? Oops, sorry. When you plug in 1 in here, f of 1, you get negative 3, right? But if you plug in 1 into 2 f of x, then what do you get? You will be getting 2 times 1 squared minus 4. So what is that? You will be getting negative 3 times 2, hence negative 6. So as you can see, your negative 3 turns into negative 6. That's what it means. All right, your y values get doubled up because 2 is multiplied to f of x. So a causes a vertical stretch by a factor of a. Now, let's consider having x multiplied by 2. Now, well, when something happens inside the parenthesis, whether it's being multiplied or being subtracted, you can actually imagine having stretch the opposite way. Meaning, I told you if 2 is multiplied here, the entire thing gets shrunken by, it gets stretched by 2, right? But when 2 is multiplied to your x, instead of being stretched, it actually shrinks down. So that here, I actually wrote 1 over b here. It's different from before, right? So just imagine it happening the other way around. So when f of 2x is given, the whole thing gets narrower. So your function equation before, okay, this time since we are talking about the changes in horizontal transformation, right? Concentrate with the x-intercepts. Remember how we had x-intercepts at 2 and negative 2 before? These values will be multiplied by 1 over b. In this case, 1 over b is 1 over 2. Okay? So that basically what happens is that your x values will be halved because there is a 2 in front of x. So your x-intercept will be at negative 1 and at positive 1. What about your y? Nothing changes for your y. Your y will still be at negative 4. So as you can see, instead of being stretched, it got narrower. Okay, that's what it means by shrink and stretch. It's actually the opposite way around. It stretches, it actually narrows it by factor of a and by factor of 1 over b. So simply just imagine having your x being divided by b. Okay? Now, next, horizontal shift by c. When x is subtracted by a number, the graph goes to the right by it. Well, consider c as a positive number. So basically, if your x is subtracted by 2, your graph will be moving to the right by 2 units. If your function is added by 2, then it's technically going to the other way. Okay, so minus 2 means to the right, plus 2 means to the left by the given units given by the value c. So if we still, well, let's consider the same graph again. So if you have your functions graph, x squared minus 4, okay, here we go. What will happen when your x is subtracted by 2? Again, what did I say before? Your function will be moved to the right by 2 units. So what is moving? Whoops, my bad. Just x squared only. So how do we move this? By 2 units. So what is moving? It's horizontally moving. So technically, what you can move here is your vertex. Isn't the vertex here at 0, 0? Let's move this by 2 units. Where does it go? The vertex goes to right here. It goes to 2, 0. So it still is the same looking graph because, you know, we didn't have to shrink it or stretch it. It's just simply being moved, slided to 2 units to the right, so that you will be having the same graph but over here. Okay? So horizontal shift, the only thing that you have to worry about, you know, is remembering, you know, how the sign is swapped. Because if, you know, usually when people see a plus sign, they usually imagine this being added, right? But for horizontal shift, it's the other way around. So again, if it's added by 2, it's actually going to the left, all right? Subtracted by 2, then it is going to the right. Just remember that part, then you'll be okay. Now, well, finally, the vertical shift. The vertical shift is actually easier than the rest of it. Well, that's what I think, at least. A vertical shift basically means that your y value is being added by whatever your function is added by. Hence, everything will be going up or down by whatever whatever the value d is. So, you know, unlike the previous one, if your function is added by 3, then the function d graph actually goes up by 3. And if it's being subtracted by 1, then it actually goes 1 unit down by 1. That's all. So you can just simply follow the sign and the value for vertical shift. So, okay, let's just use x squared. So if we use x squared, when 2 is added, then your vertex, you know, it's just that the vertex is the easiest point for us to show people how your graph is moved. That's why we usually use the vertex or the, you know, x or the y-intercepts. And so if you just remark your vertex for this graph, since you have to go up by 2 units, your vertex will now be at 0, 2, right? And again, like before, there was no stretch or shrink. Hence, you still have the same looking graph, just, you know, move it by 2 units above, you know, from the x-axis. That's all. So those 4 are the simple function transformations. So the first 2 shows how you can vertically or horizontally stretch or shrink the graph. The third and the fourth shows the shift, how you can translate your graph to the left or right, or to above or below. That's, you know, what the first, you know, section of the transformations are about. But this is not the end of it. Unfortunately, there are more. And wait until you see them, you know, being mixed all together. Students are usually confused when your functions are like, you know, like translated as well as, you stretched. That can be really confusing if they are mixed up. So okay, before we move on to the next section, why don't I just show you what you need to do when they're mixed up. So I know I changed my function for the last two, but let's go back to what we initially start off with. So consider this as the function. Now, let's try doing 2 times f of x minus 3, right? So basically, this and this, well, I mean, they're both, what kind of transformation is it? Is it like horizontal transformation or vertical? Well, a simple way for you to know whether it's vertical or horizontal is, it's based on seeing whether the value is being added or multiplied inside or on the outside of the parenthesis. Okay? So technically, if something is going on inside of the parenthesis, it means that your function is transformed horizontally. If it's outside, then it's being done vertically. So the 2 is a vertical stretch, all right? So this is a vertical stretch by a factor of 2, and this will be done vertically as well, and that is the shift. Hence, what is going on? It is actually going down by 3 units. So just understand what these are going to cause to your function and just apply it. How? Start graphing it. Again, since the vertices of the vertex or the intercepts are the best points for you to show people how they are moved, just mark your vertex and the intercepts. And now let's apply. Well, by the way, guys, stretch first and then shift. So stretch this by factor of 2. So remember before, it's same as before, right? You have to have a little bit longer down here. Okay, you will have to have on y-intercept of -8 now. Your x's are still here and here. So here we go. Your function is vertically stretched. Oops. Okay, here we go. I'm sorry, I'm not very good at drawing. Okay, so the white bit shows how vertically stretched the function graph is. Now, then, apply the translation. This means that this will have to go further down. So, if I just may redraw this on the next grid, here we go. So, you will be having your x-intercept at -2 and +2, but your y-intercept, well, here we go, after 2f of x, right? And your y-intercept is at -8, right? But this whole thing will have to shift down. So, okay, so first of all, where does this go? This point, guys, is technically at -2, 0 now, right? But this is going down by 3 units. So that this point is going down by 3. So here, let me just get here. And then this point too is going down by 3, so that now you'll be having points at -3, -2, -3, and +2, -3, right? As well as -8, your y-intercept will be going down by 3 units as well, so that you will have your y-intercept now where? At -11. So it's kind of messy now, but it goes like here, here, here. So the shape is the same, but it's all entirely stretched down by 3 units. So it's just that whatever you're doing, whether you're like showing people how they are transformed in school or in an exam, just make sure that you at least show 1, 2, 3 different points, okay? So that so that people know what you did with your previous function in a graph. And hence, you can show that you did everything you're supposed to do by showing a few coordinates for the new graph given. So 0, -11, -2, -3, +2, -3 are the 3 new points for your finalized transformed graph. So again, I hope you remember that I said previously that you should stretch first, then shift. Just remember to shift later, then you'll be fine. Okay, now we will do a little bit more complex transformation now. Okay, now because I'm gonna show you horizontal and vertical being done at the same time. So are you ready? So let's do f of 2x minus 4 plus 1. Okay, now, for me, I actually do prefer doing this. Can you see what I did? I didn't really change the function notation. All I did was I factored the 2 out because they, because there was an 2 in front of x. And the reason why I did that is actually to do the translation later. I will show you, what I mean with the graph in a minute. When you rewrite an equation in this way, so whenever you have a coefficient for your x inside the bracket, when you factor that coefficient out, then it actually can, let you do your transformation in this order. Stretch first, then shift later. Okay, so do this, then you may shift as your final step. Okay, here we go. So what you have to do is start from the previous graph. 2, -2, -4. Now, so what do we do? What kind of stretch is this? Is this actually stretching? Remember what I told you before? If your x is multiplied by a number, it actually causes a shrink, remember? It doesn't get wider, it actually gets narrower by 1/2. So your x's will be halved. So you will be having values at -1, +1. However, the y still is at -4, at least for now. So what I did was I just stretched. So this is step 1, stretch. So this white graph shows f of 2x technically, right? Then you may shift. It doesn't really matter which one you do first. You may apply the -2 first. Should we just do that? Okay, so being subtracted by 2 meant what? Left or right? Remember the opposite way for inside the bracket, right? So it's subtracted by 2, but you are not moving this to the left. You are actually moving this to the right. So your stretched or shrunken graph will have to move to the right by 2 units. So your x-intercepts will each move to the right. Hence, where is your -1 going to? Okay, here, different color. Ready? So -1 will be going to 1, 2 steps, +1. Where is your +1 going to? That too will be moved 1, 2 units. Hence, it's going to be at 3. Finally, where is your 4, -4, the y-intercept going to? Well, technically, y-intercept is when x is equal to 0, right? So technically, your x value is 0. That 0 goes to 1, 2, 2. 2, -4. So now these are the new points of your translated function equation, right? So here we go. Let me just regraph it. So your x-intercepts are now at 1 and +3. Your vertex now is at 2, -4, right? That is your graph. And then finally, what you can do is, here we go. Let me just show you this a little bit better. All right, here we go. So this is 1, 3, and new vertex. Now, are we done? Well, almost. We still have one more translation to apply. This one, +1. Isn't that the easiest? Why? Because for this one, we just simply have to push this up by 1 unit. And up by 1 unit means what? It means that your y value will be added by it. So your x-intercepts will all go up by 1 unit. So your new points are now at 1, 1 and 3, 1, okay? And this is going up by 1, so your new vertex is going to be at 2, -3. I know the picture is not very pretty. It's not, 100% accurate. But since I showed, 3 different coordinates that lies for the new transformed graph, this is, good enough graph for any exam or any homework. So just remember, you should take your steps one by one. First of all, factor out the coefficient of x, then stretch, apply the stretch or the shrink first, then do your shifts, okay? You shift last. Just remember that. And again, at least show 3 different points for your new transformed function graph. Okay, now we'll be talking more about different transformations. There is, well, a reflection, and well, there are other things that you need to learn how to do. Okay, so the second section of function transformation shows reflection. So when negative is applied, it actually causes reflection. By the way, negative f of x means that your y, right? Because isn't f of x the y value? Is being negative y. So your y, say if you have a positive y, right? What happens when that turns into negative value? It goes down here, doesn't it? So hence, your function flips about the x-axis. And for the same reason, sorry about that, guys. Just ignore that. It's just negative x here. F of negative x. When your x turns into negative x. Now imagine if your previous x was positive value, right? What happens to the point when that becomes negative? Doesn't it go over there? So what is going on? It gets reflected about the y-axis. Remember, guys, outside x, a negative, means that reflection over the x-axis. The negative sign inside means reflection over the y-axis. Here, with an example graph, let's just go over this one more time. So if you have a graph, it's like the 5th time me drawing this. Here we go. Okay, so if this is the function equation, what do we have to do when negative f of x is given? The entire thing flips about the x-axis. So simply, your intercept will stay. And what will happen to this value? Isn't that the y value? Negative, right? The signs change. Negative, negative is positive. 4. So the entire thing, this part flips up. Yeah? And what about this part? It was positive. It will obviously become negative now. So just flip it, flip the bottom part up and flip the up part below. So that is your new transformed graph. Now, for my function example, it's not a very good example for this one because as you can see, look at this. The original function actually is an even function. Remember what we said before about an even function. Even functions have symmetry about the y-axis, so that even if you do reflect over the y-axis, nothing will change. So look at this. The initial function and f of negative x are the same functions. So you can't really see the difference here, but just please remember, negative means that you will be reflecting about the y-axis. Okay? So here, if I just if I may, here with some other function graph. So if we have a graph over here instead, right? For example, if this is f of x, then when you plug in negative inside of the bracket, then this whole thing will be flipped over to the other side so that you will be getting a curve, parabola curve over here instead. Okay? So this flipped over to the other side. That's the transformation caused by negative sign in front of x. Now, the last one. By the way, this is just a review of what we have talked about previously. So let's talk about the last function transformation. The last function transformation is given by the absolute sign. What does absolute sign mean? Absolute sign of a number. Do you remember what absolute value basically meant? It meant the distance between the value and the 0, right? The origin, right? So technically, when you plug in a number inside the absolute value symbol, you know, we just remember it as like the numbers become positive, right? Well, technically it's because we are measuring the distance. So that obviously the distance of a number is always positive, right? So your y values, if you think about it, will all become positive. So if it was already positive, it's not a problem. But if you had some negative y values, right? When you put absolute sign around it, every negative value becomes positive. Hence, this too becomes positive, right? What about values over here? Don't they all have negative values? When you put absolute sign around it, they all become positive. Hence, the entire part, again, gets reflected over the x-axis. So the part that was negative for the y, becomes positive. Hence, they go up by over the x-axis. But what about the remaining part? What about these parts? Aren't they positive? So, like say, if there is a y value of 5, isn't absolute value of 5 still 5? So for positive y values, they still stay where they are, or where they were. So nothing really changes for the positive part. The only part that changes is the negative part. So just remember this. For absolute functions, for absolute value of a function, the graph reflects, but not the entire graph reflects. Only the part that is below the x-axis reflect. The remaining part stay as where they are. So again, if you have a function graph that goes like this, then the negative part, this part and this part, those flip up. So you will be getting, here, let me show you in red. So you will still get the positive as positive, but this part flips up. Hence, this is what you get. Positive stays as positive, and the negative part flips up. So this is what you get. Positive stays positive. All right? So here, before too. Positive stays positive. Negative goes up. Positive stays as positive. This is what the transformation for absolute value sign causes. Okay, now, for the last part, this is the part when everything's mixed up from the previous, page. A, B, C, D. For A and B, it causes what? Stretch or shrink. For C and D, they just slide the graph around. What do we do first? We stretch or shrink first, then we shift last. Just don't forget the rule and you will be fine. And reflections and reflection, I actually think that this is really, really fun because you're only reflecting the part that is negative, so that whenever you reflect, or sometimes when you reflect it, you actually get a funny looking shape of functions. So this is the end of function transformations. And well, thank you for listening. I'll come back later with more functions.